Well, now we are going to continue with the talk by Federico Ardila from San Francisco in the USA, and he will speak about inequality for tree and matroids.
Thank you so much to the organizers for putting this beautiful event together. I know you've been working very hard to make this happen, and for us it's really wonderful to come to Rio and see old friends and new friends and talk about mathematics. So thank you so much for that. It's always a pleasure to be back in Rio, be back at IMPA. Yeah, my plan for today is to tell you about a very new project. So this project is, in some sense, still ongoing. What I'm going to tell you is about 1 month old. And so my plan is to give a very imperfect but honest talk about where we are with some mathematical stories that I find quite interesting. The subtitle of this talk could be called Federico Learns About Lorentzian Polynomials. Because I don't know about you, but when I go to talks and other people talk about their beautiful mathematics, I appreciate it, but I never feel like I quite understand it until I sit down and try to do something with those tools. And so in some sense, what I'm going to tell you about is a story that started somewhere else, where we ended up using some tools from Lorentzian polynomials to prove, and some tools from other parts of mathematics to prove some inequalities for trees and matroids. Everything that I'm going to be talking about is joint work with Graham Denham, Kris, Juni He, and Botong Wang. Okay. So first, let me tell you a bit of by now a little bit old story of Graham and Pollack on distance matrices. So this is a paper that I find very beautiful by Graham and Pollack, who were researchers at Bell Labs in New Jersey. So Bell Labs was the telephone company. And I learned more about the telephone company than I ever thought I would. And I guess at the time, Bell Labs had a monopoly over the telephone system all over the US, and they were really in charge of connecting the phone calls around the US. Graham and Pollack were interested in optimizing that communication. It's funny because they talk about how, the system of the Bell system has been working fine, but now there's these new things called computers that are demanding a different kind of speed. And I guess with phone calls, all of us were used to waiting for somebody to pick up the phone, which gave time for the system to take its time also and hide it behind, pretending that the other person was not answering the phone yet. But now computers were demanding faster processes, and so they were looking for faster algorithms to route calls. And so they start with a graph. And so let's go over here to some graph G, which, of course, I'm doing a very small example, but you should really think of G as the telephone system of the United States. Okay, so I have to say that this is written in an internal report of Bell Labs, and they assume that you know how the Bell system works, and I don't know how it works. And so I have to make some guesses, but what I understood is that the nodes are basically, like our phones, and then they're kind of connected in some way, and then if this person needs to talk to this person, then they need to kind of route the message around. Then what they're thinking is, of course, this is a very, very large system, and so they are trying to come up with addresses for the nodes, which I think of as phone numbers. I have to confess that I don't know how accurate that is, but for me it's useful to think of these as phone numbers, so I'm going to assign a phone number to each node. Okay? Now these phone numbers should somehow reflect the structure of the graph. Okay? So the graph is connected in this way. Here I have what they call the distance matrix, and this is just the entry CE is the distance from C to E in the graph, number of edges. Okay. So Aij is distance from I to j. So this is a symmetric positive matrix, zeros in the diagonal. And now what they're interested in doing is somehow, one way that I can think of it is endowing it with a little bit of geometry. So they're giving it these addresses, and I don't know if anybody has been able to see the pattern yet, but the idea is that these addresses should reflect these distances. Okay? And so the first idea that they had is, why don't we try to give 0, 1 addresses? And in such a way that the Hamming distance, so the number of places, the number of positions where the addresses differ, should be the distance in the graph. Okay? In other words, the question would be embedding this graph into the hypercube, the 0, 1 cube. You quickly realize that this cannot work, because if you have a triangle in a graph, hypercubes don't have triangles. So right away, that's not going to work. But then they say, okay, let's add a little bit more flexibility. Let's allow zeros, ones, or stars. Okay? And so here, each address is a string, the same length of zeros, ones, and stars. And the star is kind of a joker that can pretend to be a 0 or a 1. Okay? And then the idea is that the Hamming distance, for example, between B and F, is going to be how many positions are there where the coordinates are 0 in one position and 1 in the other. In other words, stars don't contribute distance. The distance is just the Hamming distance between the zeros and the ones. Okay? And so last time I gave this talk, I did this spectacularly horribly, and in the example, nothing was correct. This time I double-checked, and I think everything is correct. So please feel free to double-check that the Hamming distance, if you forget the stars, should match here. So you can check that while I write this down over here. So,
just a quick remark. This graph there is not the same one in the line of hope, right?
I'm sorry?
There are 2 graphs on the backboard.
Oh, that's a good point. This is Ron Graham, and this is Graham Denham. Yeah. So goal is to give 0, 1 star addresses to the nodes of a graph so that the distance in the graph between any 2 vertices is equal to the what we might call the Hamming distance, although this is not quite Hamming distance, between the addresses, which I'm also going to call U and V. And here, the idea is that so this is the number of positions I, such that Ui and Vi are 0 and 1. So one of them is 0, and the other one is 1. And stars you ignore. Okay? This is their goal. So any questions about that setup? Because that's what I'm going to be concerned with for the next little bit. So find or estimate the number ng, which is the minimum possible length of the addresses. So if you think about this for a little bit, you'll find that if you use really long addresses, you're going to be able to do this. And the question is, how can you do this with the most economical addresses possible? We know that long phone numbers are not fun to dial. So that's what they're interested in computing. Okay? So let me show you how they approach this. I find this incredibly beautiful. So they show that this number is at least the maximum of the number of negative eigenvalues and the number of positive eigenvalues. of the distance matrix. This is negative eigenvalues. And these are positive eigenvalues. Okay. Which is very surprising. This is combinatorial. This is linear algebraic. So let me sketch a proof. By the way, let me say something. We never finish learning linear algebra, right? Every time we realize, oh, I didn't know linear algebra. And so I'm going to review things that you probably know, or maybe you don't know, and I actually learned a bunch of new linear algebra here. But for example, just something that I think you know, but you might have forgotten, is that a symmetric matrix has real eigenvalues. Right? So therefore, they're either positive, negative, or 0. And that's why this makes sense. OK, so what they do is this. They say, instead of, so another kind of classical trick in linear algebra is to pretend that a matrix is a quadratic form. So I'm going to take the entries of the matrix and make a quadratic polynomial out of them. Yeah?
Can you repeat what NG is?
By definition, it's the minimum possible length of the addresses that you can do so that the distance in the graph equals the distance according to the addresses. So for example, there I gave addresses of length 5. And I'm trying to see if I might be able to have shorter addresses. And this is telling me that that actually depends on the eigenvalues of that matrix. Okay, so this, if I did it correctly, should be equal to the Hamming distances, like this. Okay, but now here, I can write this as a sum from I equals 1 to the length of the addresses of the following thing. The sum of over the variables where ui is 0 times the coordinates where vi is 1. Okay. If you look at this, when are you going to get a contribution of xu times xv here? You're going to get it whenever the ith coordinate of u is 0 and the vth coordinate of v is 1. And I want to put a 0 here and 1 here so that I'm not double counting. Okay. So that's an equation. Now let me call this I and ti. And then they say, look, this is the sum from I equals 1 to n of Si plus Ti over 2 squared minus the sum from I equals 1 to n of Si minus Ti over 2 squared. So it's just a simple algebraic manipulation. But why is this interesting? Because now you're taking a quadratic form and you're expressing it as a sum and difference of squares. So for example, if you manage to express this as a positive sum of squares, then you would know that this is a positive definite form, therefore a positive definite matrix. The linear algebra that I didn't know and I learned is that when you have something like this, then you get some bounds, that basically the number of terms here is bounded by the number of positive eigenvalues, and this by the number of negative eigenvalues. And this is Sylvester's law of inertia. Okay. So because this form can be expressed as sum of n squares, and here I mean squares of linear forms in the x's, minus the n squares, then Sylvester's law of inertia tells you that this is greater than or equal to n plus, and this is greater than or equal to n minus. I get that. Okay. So that's a sketch of the proof of why the eigenvalues of this matrix are actually interesting in this very, very concrete addressing problem. Okay. So they do this, and then they say, okay, so if you know something about Ron Graham, so Graham in some sense was a disciple of Erdős, and whenever there was something that he couldn't do, what he really wanted to see done, he would conjecture it and put a price on it. And so there's a $100 conjecture. And if you know this part of combinatorics, if you solve a Ron Graham conjecture, you cash that check. You don't cash that check. You put it on your office wall, right? And if it's a $100 conjecture, that's a pretty hard problem. So he has $1 conjectures, and then he has like $10,000 conjectures, and 100 means that he tried, and this is really not easy. The conjecture is that this number is at most the number of vertices minus 1. That's the conjecture. I would argue that we know a lot more about matrices, signatures of matrices, and so on, and it probably is worth trying this again because I think we have some new tools. Okay. This is from that paper of Graham and Pollack, but then they prove this theorem that equality holds for trees. Okay, and this is what I want to talk about. Let me also sketch a proof of this. Okay, I'm going to show both inequalities. This inequality is constructive. It's saying you are able to address a tree with v minus 1 length. And you can imagine this is not hard because trees don't have cycles, and you can kind of just do it in pruning order, and it works out. So you try it, and it's going to work. So you construct it carefully. And I had never done this kind of problem, and I found that I could sit down and do it. For the other one, they want to prove that NT is at least v minus 1. And then they say, well, we have some ways of bounding that through eigenvalues. And so what they say is, why don't we try to figure out what are the signs of the eigenvalues of these matrices? And if you were in the, so you were creating a suspense arc that I think I can now write your suspense arc, because we somehow want to say that ideally this number is v minus 1. This is a v by v matrix, and we want this number to be v minus 1. So probably what we're trying to prove is that v minus 1 of these eigenvalues are positive or negative, and when I look at it, it looks more positive than negative. So that's what we're going to do. Okay. So the claim is that the number of positive eigenvalues is exactly v minus 1, and the modern way of saying this is that this matrix is Lorentzian. It has v minus 1 positive eigenvalues and 1 negative. So I think it's very beautiful that Lorentzians came up already. This is back in the 70s in this very concrete situation. Okay. So, okay, how do you figure out the signature of a matrix? This is another part of linear algebra that you might have learned and might have forgotten, which is that you can find out the signs of the eigenvalues by looking at the principal minors and seeing how they alternate. Okay. And this is Cauchy's interlacing theorem. This is an application of Cauchy's interlacing theorem, which I have to confess that I didn't know actually until but I did know this thing that right, I think I might have this backwards actually.
Yeah, I think that's more negative.
Yes. Yes, that's right. And so in order to show that this thing has a lot of negative eigenvalues, what I need to show is that the sequence of principal minors alternates in sign a lot. Because the number of negative minors is the number of times that so the n minus is equal to the number of sign alternations of principal minors. And this is really very explicit. The first principal minor is this, the second one is this, and you look at how they alternate. And so in particular, this means that we should know something about this determinant. And so this determinant, but not in the general case, but in the case of a tree. And what they found is a very beautiful formula for the determinant, which is equal to -1 to the v minus 1, v minus 1, 2 to the v minus 2. Okay. Which is pretty amazing because this really doesn't care what the tree looks like. It's telling you every tree has the same determinant. It's a very beautiful formula. Now that you know it, you can prove it. Sit down, prove it. You can do some kind of recursion. It's not very difficult to prove, but it's a very remarkable result, I think. Okay? So that means that you know the sign of the big determinant. It has sign v minus 1. But then you say, oh, okay. Here's my matrix A sub t. And now this determinant I know. Now I want to know what this determinant is. Okay? But you have freedom here, which is that you actually are able to switch rows and columns however you want. And so what I'm going to do is that I'm going to put a leaf here. A leaf of the tree. So that means that if I take this out and take this out, I just plucked a leaf off of the tree and it's still a tree. And so the formula is given by this with b minus 2. And then I put another leaf here. And so this is what people in some neighborhood of computer science call pruning order, which is very beautiful. It's a beautiful name. English is not my first language, but pruning is like cutting a tree. You take a leaf, you take out another leaf. And then each one of these determinants is given by this formula. So the minors are, the first one is the empty matrix. The second one is 0. Then minus 4, then 12, then minus 32, and so on. So this alternates v minus 1 times. And that proves this result. One thing that I find very beautiful about this is that this is the only proof that we know of this very combinatorial question. How can you embed, what is the smallest, they call this a smashed cube. So it's not the hypercube, because you have 0, 1, and the star is like you squash the edge from 0 to 1. So what is the smallest smashed cube that you can embed a tree in? This is the only proof that we know. This is actually in Ziegler's and Eigner's proofs from the book. Yeah, so I find it beautiful, and it's interesting to me that the Lorentzian is kind of, it plays a central role here. Okay?
Instead of squashing the hypercube, can you see these V's as faces of the hypercube?
That's how I prefer it, yeah.
And look at the distance between faces?
Yeah. They call it a smashed cube. I wonder if that's what they meant, but yeah. Yeah. I should say this is actually strictly Lorentzian, in the sense that the eigenvalues are v minus 1 are negative and the other one is positive. No?
No, it's a 0 eigenvalue, and I think it's a 0 and minus 2.
Wait, but 0 is an eigenvalue of this tiny one, but not of the big one. Yeah. But thank you, and I mean, I already confessed that this is an imperfect talk, and I hope I make some mistakes and you can fix them. Okay, okay, so that's part one of the talk, is just kind of saying one story of how that matrix is interesting. Okay? So now let me tell you. So I'm telling you this story in a way that is maybe historically correct, but not accurate to how we discover these things. So actually, I learned about these things while I was preparing this talk. Last time I gave it just cramming for a talk, and I found this story. But we actually ran into that matrix in a very different context. So let me tell you what our...
The interlacing inequalities for eigenvalues define the Gelfand-Settling polytope. I was wondering if that polytope appears in your combinatorics or not.
I would really like it if the Gelfand-Settling polytope played a role, because I like that polytope very much, but I don't know of a way. It could be, yeah. I think I see what you're saying. It would be fun to talk about it, yeah. Okay, so let me tell you what are our results on distance matrices of trees. So now let me start with a tree T, but I'm going to be a little bit more general and allow the tree to have edge lengths. Okay? So this is what we call a metric tree with n leaves and edge lengths that are greater than or equal to 0. Okay? And I'm going to define a matrix which is almost AT, but it's a little bit smaller. BT is going to be the matrix AT, but restricted to the leaves of the tree. Okay? So I don't care about the pairwise distances of all the vertices. I only care about the distances between the leaves. So I'm going to call this the leaf distance matrix. And that's why I left a little space here. Okay? So let me make some comments about this. So one corollary is that BT is also Lorentzian. Okay? And the reason for that is that it's a principal minor of AT. And Lorentzian properties have Lorentzian matrices have the property, and I didn't know this, that if you have a Lorentzian matrix and you look at the top corner submatrix, that's also Lorentzian. That makes sense actually because the principal minor criteria. The alternations still happen in the same way. Okay? And it may be that here I pick up a 0 eigenvalue. So I stop being strictly Lorentzian, but I'm Lorentzian. Okay? Now, let me make a couple of comments. Metric tree or not metric tree, it's actually not a really important thing because if you have an edge of length 3, then you could introduce intermediate vertices. And if they're fractions, then you can put a common denominator. And if they're irrational, you can take a limit. So somehow, the fact of being metric or not metric is not too important. And the other thing that I want to say is also that A matrices are B matrices. So one thing that's what's most important is that these things are also Lorentzian. But I also just want to point out that if you have the A matrix of a tree, then you want the pairwise distances between all the leaves, between all the vertices, but you can just make this trick where if you're not a leaf, you can make yourself a leaf by just sprouting out here something of length 0. And now basically this internal vertex becomes a leaf. So put a 0 here, put a 0 here. So by going from the vertex t, from the tree t to the tree t plus, you get this. So A and B are really pretty close to each other. Okay? And so for the rest of the talk, I'm going to focus on the matrix B. That's the one that's interesting to us. Okay. And with that, I'll write our main theorem, and maybe I'm going to write it over there to see if maybe I need it later. So our main tree theorem, and this is the list of authors that I said, with Graham Denham, Kris, Jun Ho, Bo Tong Wang, is the following. It has two parts. For any, so I'm going to say a theorem about trees, but I'm actually going to focus on a family of trees that is rooted. Okay, so there's a root, and that of course is not a restriction. You can root any tree just fine. Okay, so I'm going to put a root, and then I'm going to get a tree like this. And the other condition that I'm going to impose is that it's equidistant. And what this means is that the distance from the root to a leaf is always 1. And again, this is not a huge restriction, because if it's not equidistant, you can make it a little longer to be equidistant, and everything is pretty controlled. So there is a version of this theorem that is not equidistant, but this version is going to be nicer, cleaner. Okay? So for any rooted, equidistant metric tree of height 1, so I take, right, so BT was Lorentzian. So it has 1 positive and the rest are negative eigenvalues. So when I flip the sign, it becomes 1 negative and the rest are positive, which is why I was getting confused. I was getting them mixed up. So this has signature minus, plus, 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 plus. And now what I'm going to need to know is how much do I need to shift this matrix up so that all the eigenvalues are positive? Now, if I add a multiple of the identity, then the eigenvalues just go up by that quantity. But what I'm going to need to know is what happens if I add a multiple of the all ones matrix. And I'll explain why this is what I need. But we need to know how do we make this positive definite? What is the constant that I need to put here? Positive semi-definite, meaning that the eigenvalues are greater than or equal to 0. And the number that goes here is 1 minus 1 over n. And that's the best number that can go there. Okay. So that's kind of telling you how far away from so you're not positive definite. So how far away from positive definite are you? And you're this far away by adding to that matrix. And this is our main tree. I'm sorry? N is, oh yeah, sorry. with n leaves. So here would be 5.
This 1 minus 1 over n is the smallest such that this holds for all trees,
Exactly.
but there's some trees where this might be still smaller number.
Exactly. So each tree has its own constant, but this is the constant that works for all the trees of that size. So the Graham-Pollack conjecture, the $100 conjecture, was about trees that are not metric. They're
I guess, but you still have some sort of metric on it once you've chosen once you put an address on everything. So it's sort of
yeah. I'm not sure that it applies directly,
okay,
but
so it's just two different
yeah.
two very different things.
Okay. So this is our main result, and if there's a little bit of time at the end, I will tell you a little bit about the proof. But I want to tell you why we became interested in this result. I mean, this is I found it pleasant after the fact that this seems to be in the same family of results as Graham-Pollack, but that's not how it arrived to us. So it arrived to us somewhere very different. Yeah?
Can this be thought of as some kind of bound on the positive eigenvalue or change data bound on the positive eigenvalue?
I wonder about that because it's something like that, right? So let me say what I so if this was the identity matrix, then the number that you should put here is just what's that negative eigenvalue? Just bump up by that negative eigenvalue. The fact that it's the all ones things makes it a lot more subtle. It probably has something to say about what that eigenvalue is, but we have not really thought about that. Yeah. So we arrived at this through Matroid inequalities. So here, okay, we've seen I don't know how many definitions of matrix, and I'm going to give you yet a different one. I don't think that any definition has been repeated, and I'm going to give you yet a different one. So let M be a matroid. I'm going to give you the independent set point of view. I have to be careful because I love talking about matroids, and I promise myself I'm going to stop, like not say too much about them. If you're curious about this, I have like 40 hours of videos on YouTube about matroids. This is not the moment. But I'll tell you, okay, so you've heard this before, but I'll repeat it. Matrices are supposed to abstract what notions of independence mean in mathematics. So it could be independence in linear algebra, independence in field theory and field extensions. It could be matching problems, it could be graphs. And the motivating examples, and if you prefer, you can just stay with these examples and forget about the abstract setting. E is a finite set of vectors. And this is the independent subsets. So just which subsets of your vectors are linearly independent with each other. And example 2 is that E is the edges of a graph. And I is the subgraphs that have no cycles. Those are called forests because they're a bunch of trees. So forests. Okay. And Whitney and Nakazawa realized that these two satisfy the same properties, which is that the empty set is independent if I is a subset of J and J is independent, then I is independent. And if I and J are independent and one is smaller than the other, then I can use something from the bigger one to make this, to increase the smaller one. Okay. And as every speaker has said, if this is the first time that you see this, don't worry about it too much. The details are only important when you try to prove things. But really, you just want to think these are the axioms that these things satisfy. Okay? But in particular, one thing that you might want to think is, okay, I have 100 vectors in R10 or whatever, and then you want to say, out of those 100 vectors, which singletons are independent, which pairs are independent, which triples are independent, and so on. Okay? And I'm going to say that I sub k is the number of independents. So this is, not just in this example, but in general, number of independent sets of size k. Okay? And so Mason had these conjectures. So the first version of the conjecture is that ik squared is greater than or equal to ik plus 1, ik minus 1, log concavity. Okay? The second version of this conjecture is stronger, which says that you can put a k factorial here in front of these things, which makes this conjecture, which makes this inequality stronger. Okay. And the third version of this conjecture says that not only can you scale by factorials, you can scale by binomial coefficients. So these are Mason's conjectures from 1972. Why do we care about such things? These kinds of conjectures, I often repeat this, that when you come up with an observation like this, either you are able to prove it that afternoon, or maybe within a week or so, or you're going to have to wait a few decades. That's kind of what usually happens. And the thing that usually happens is that these kinds of conjectures just require connecting to and really understanding something new. Okay? And so you are probably aware of at least part of this story, that the first, okay, and this conjecture, so the white conjecture, which is, this was proved by Adiprasito, Hodge, and Katz in their Annals paper, where they basically give birth to the Hodge theory of matroids. Well, maybe June gave birth to the Hodge theory of matroids in his earlier papers, and this is maybe like the first kind of comprehensive version that works for all matroids. And again, I think what's more interesting is less the conjecture and more the fact that now we have a Hodge theory of matroids. The blue version was then proved by Hodge, Shokrieh, and Wang. Same Wang, Botong Wang. And here they basically had to strengthen that theory. And again, I think what was interesting is the strengthening of that theory. And then the red version of this was done by Brandon and Hodge in this other Annals paper, where they basically give birth to the theory of Lorentzian polynomials. And so again, I think what's interesting, what is less interesting is the log concavity in itself. And what is more interesting is that now we have a theory of Lorentzian polynomials. So this is why I'm interested in these kinds of things. Okay? So we were motivated by Mason's conjectures. And the following question, due to Igor Pak. Let's say that we now let ik be not a number, but a polynomial. I'm going to agree with Alex also and make my ground set size n. And then instead of counting the independents, I'm actually going to list them and make them a polynomial. So sum over I independent of size k x to the I. So if the independent set is 2, 3, 5, then this means x2, x3, x5. Okay? And so then he asked, could it be that these polynomials also satisfy this? Now, what does it mean for polynomials to satisfy this? We could say plug in, but actually we mean something much stronger, which is that we want this coefficient by coefficient. So it's a much, much stronger statement, right? Coefficient-wise. And it sounds like Igor didn't believe this, actually, and he kind of said this is probably not true, but somebody should check it. It's a very strong statement, saying like, maybe I'll say here that what this means is that for any set S and numbers I less than j less than k less than L such that so basically if I want to write S as something of size I and something of size L, so S as the union of independents of size I and L. And if I want to write it as a union of something of size j and k, then this is always going to be less than or equal. You can look at this and think for a bit, and you're going to find that this is the same statement. So it's a statement somehow about taking a set of vectors and saying, how can I split it into two independent sets of prescripted sizes? And it's saying it's going to be better to subdivide it into two things of similar sizes as opposed to farther sizes. Okay. And so theorem is that this is true. And this is one of our main Matroid theorems. And this was so we first had a proof with Graham Denham, Kris, and Juni Ha. And here we were using the kind of intersection theory of matroids that we have been hearing about, that I think maybe we'll hear a little bit more tomorrow in Kris's talk. So we were able to prove this using that intersection theory techniques, and it's kind of Kovansky test here, inequalities and things like this. Okay. But then we also started wondering, can we put things in front and maybe try to find some new results? And we found that we also can put a k factorial here. And this is still true. So this is also true. And this is what we are doing in this new project. And here we use the theory of Lorentzian polynomials and the fact that we have signatures of matrices and so on. Okay. And what this ends up being is that you can you get this weighted by I factorial, L factorial, and J factorial, K factorial. Okay. So I think in the interest of time, I'm not going to say too much about another motivation.
Sorry, how about the red?
Oh yeah, I meant to say the red version is not true. So yeah, you have to wonder, right? So they'll put no here. The red version is not true. And so right, so this is using this kind of Hodge theory technology, and this is using this kind of Lorentzian technology. Okay?
So sorry, what red? The red one follows from your more generalistic, from this polynomial equation. Or doesn't?
I don't think.
By specializing x to some function.
Yeah, actually, okay, I want to be careful, but what we do here is a strengthening of what they did here. So I'm pretty sure that the blue version of this is going to imply the red version of that. Let me just say one more thing, which is that we had another motivation. So which was this question of Pak. But we also had this question of Giansiracusa, Rincon, Schleiss, and Uller's conjecture, which basically is a version of Mason's conjecture that holds for valuated matroids. Mason holds for valuated matroids, or if you prefer, you can say points on the tropical Grassmannian. There's technicalities that I'm sweeping under the rug, but it's a richer version of this. And they actually proved the white version and they conjectured the blue version. Okay. So theorem is that this is also true. Okay, so we were able to prove this. And if you're interested in evaluated matrix and the details of that, I'm happy to tell you afterwards. I think I won't say too much about it, but maybe what I want to say is that, and maybe this is in some sense an answer to Anna's question in the previous talk. So you were saying, Oliver, and you're right that, I think you understand this better than me, that it's pretty tricky to check that things are Lorentzian. So it's a wonderful technology, but if you want to show that some sequence is Lorentzian, you need to kind of embed it in some kind of family of things that has this inductive behavior. And the architecture needs to be just right, and if the architecture is right, it's beautiful and it's very simple. But there's a lot of work in kind of carefully constructing that architecture. And it turns out that this is the most general setting where we actually, this is the architecture where we show Lorentzianness. Lorentzianness in this setting is what we use to prove these conjectures. And I'll just say in a couple of words that as Oliver was referring to, if you want to prove that things are Lorentzian, you kind of do this inductive thing until it becomes degree 2. And so basically, if you want to show that these kinds of things are Lorentzian, you inductively end up needing to do it. So you induct, and the inductive part is actually quite simple. And then you have to do the rank 2 case. You have to check that one directly. But then there's this very beautiful fact that rank 2 valuated matroids are basically trees. They're metric trees. And so when we need to check, okay, during this architecture, we get the rank 2 case, we need to check that something is true for metric trees, and we ended up checking that what we needed to be true for metric trees was that theorem. And that's why we proved that theorem. Okay? So is this connection with rank 2 evaluated matrix? This is the same as talking about the tropical Grassmannian 2n. So you might be aware of that story, that this is very much about the geometry of the tropical Grassmannian 2n. And maybe the last thing that I'll say is that one reason that I felt lucky here is that because I have some older papers on tropical geometry and phylogenetic trees, it turns out that there's this story that connects general trees to equidistant trees. And it turns out that equidistant trees are the same thing as points in the tropicalization of the matroid of the braid arrangement. Or if you prefer, of the root system. So to any set of vectors, you get a matroid. If you put the root system of type A and you tropicalize it, you get exactly the space of equidistant trees. This is something that we have proved with Carly Clivens in 2006. And so we had some tools to prove things about equidistant trees, and that allowed us to prove this result. And I think that's a good place to stop. Thank you.